Okay, so what you need to know about the natural base e is it's an irrational number like pi. And it's defined as what I just explained to you. So it was defined as this guy thinking like, what if I could compound money continuously every single instant, meaning that it compounds like an infinite number of times in a year. And what happens is you're basically approaching this value of e. Now, so it's just a number. Keep that in mind when you're doing problems with e. It's just a number, it's not a variable. So we can use it with expressions. Let's say simplify. Exactly like we used numbers last unit. So if we have e to the third power times e to the sixth power, that should be e to the ninth power, because you're multiplying things that have the same base. So you add the exponents together. If you've got 16 e to the fifth power over 4 e to the fourth, you simplify it just like we did last chapter. So 16 divided by 4 is just 4. And if we have 5 e's on top, 4 e's on bottom, you're left with 1 e on the top. So this is the same as 4e. Or if we have something like 3e to the negative 4x squared, again, you do exactly what we did last chapter. You'll distribute the exponent. So this is 3 squared and e to the negative 8x, because you're multiplying the exponents together. That's 3 squared over e to the 8x, which is 9e to the 8x. All right, and the graphs look very similar to the graphs we saw yesterday. So you can see they have that same basic shape, e to the x. When x is positive, it goes up to the right, and if x is negative, it goes down to the right. Now, as far as graphing this, I'm never going to ask you to graph it just by hand. You should use a graphing calculator. So use a graphing calculator or Desmos. To sketch a graph. And I'll show you what I mean by sketch a graph in a little bit. But since e is a weird like decimal, you're never going to get nice points on your graph, basically. So graphing by hand is very tedious and not worth our time. An important thing to note, though, is that the domain is going to be all real numbers always. And for the range, you're going to check the graph. Am I going too fast? Yeah. All right, now to the interesting part, the money stuff. So yesterday we talked about compounding, the compounding interest formula, and the compounding interest formula was A equals P1 plus R over N to the NT. But there's a special case of compound interest. And that special case is exactly what that guy in the 17th century was talking about, was what if you could compound every instant? And what that's called is continuous compounding. So most banks actually use continuous compounding. They're not actually calculating using the first formula we learned. They calculate using this continuous compounding formula. And then at the end of each day, they drop in the interest that you made that day. And the P is still your principal, the rate is still R, and T is still time. So there's one less variable because there's no N, there's no like number of times it compounds a day or a year. N is just like infinity, so that's why we have E there. Now let's do an example with it. Let's say you have $1,000. Which account is better after 5 years? A continuous compounding account with 4% interest, or a monthly compounding account with 4.2% interest. Alright, so we're going to do like two equations. We'll do one for the monthly and one for the continuous. So the monthly is what we did yesterday. That's just 1,000 times 1 plus 0.042 over 12 to the 12 times 5. So we're using that formula from yesterday up here to solve for the monthly, or the monthly compounding account. And that'll be $1233.23. And then for the continuous, we're just going to plug in to our continuous equation, which you can see is at the top there, PE to the RT. So that's 1,000 E to the 0.04 times 5. $1221.40, so the monthly is better. Alright, I want you all to find on your calculator, so again, take your calculator in hand. If you need to do like e to a power, if you press the blue button second, and then to the left of 4, you'll see an ln button. And over it in blue, you see e to the x power, right? So that's how you get e to a power on the calculator easy. So that little e to the x in blue is the best way to get to it on the calculator. All right, any questions on that problem? Okay. All right, so in one, we're just going to have a few practice problems, and then I'll let you guys get to the practice on big ideas. But first, we're multiplying e's here, e to the negative 9, e to the 12th. So since you're multiplying and they have the same base, you add the exponents, so this is e cubed. That's that simplified. What's a common factor between 25 and 35? 5. They're both divisible by 5, right? So this is the same as 5 divided by 7, e squared e to the 7th. And then if there's 2 e's on the top, 7 e's on the bottom, you're going to be left with 5 e's on the bottom. So this is 5 over 7 e to the 5th. And this is all stuff we practiced last unit, guys. You're just applying the same rules here. So for the next one, distribute that 5 to both exponents. So this is 2 to the 5th e to the negative 15x, because 5 times negative 3 is negative 15, times 2 e to the x plus 1. Alright, we can combine the 2's because they're the same base, so this is like 2 to the 6th power e to the negative 15x plus x plus 1. And you can add the exponents because you're multiplying the same base. And then 2 to the 6th power is 64. And negative 15x plus x would be negative 14x plus 1. Okay, if I wanted to write the 4th root as a power, does anyone remember how to do that? What power is the 4th root? I mean, almost everyone got this one on the test, so you guys must know. 1/4. Right, so 4th root is the same as the 1/4 power. So you can rewrite this as 16 e to the 24x all to the 1/4 power. And then distribute the exponent to both pieces. That's 16 to the 1/4 e to the 24x times 1/4. And 16 to the 1/4 power is something you can do on the calculator. It's just 2. And then 24 times the 4th. That's like 24 divided by 4. So that is 6x.